Beyond the heliopause lies the Oort cloud, a hypothetical sphere of icy bodies that surrounds the entire solar system like a cosmic shell. It is believed to stretch from about 2,000 AU to possibly 100,000 AU, more than a light-year from the Sun. Though no spacecraft has ever reached it, the Oort cloud is thought to be the origin of long-period comets, those icy visitors with orbits lasting thousands of years. The objects in the Oort cloud are the ancient remnants of the early solar system, small frozen bodies that were flung outward by the gravitational chaos of the giant planets. Here, gravity is so weak that these objects are only loosely bound to the Sun and can be perturbed by passing stars or galactic tides. Studying the Oort cloud directly remains a future ambition. No current mission is capable of reaching it, but its existence helps scientists understand the architecture and evolution of our solar system and the mechanisms by which comets are delivered to the inner solar system. This far from the Sun, our solar system blends seamlessly into interstellar space, a realm filled with unknowns. It is in this deep cold where the journey to other stars begins. The nearest star system, Alpha Centauri, lies over 4.3 light-years away. Even the fastest spacecraft built by humanity would take tens of thousands of years to reach it. But the dream of crossing that immense gulf remains alive. Projects like Breakthrough Starshot aim to one day send ultra-fast probes to neighboring stars, using powerful laser sails to accelerate them to a significant fraction of the speed of light. These missions are still conceptual, but they represent a new kind of thinking, not just exploring our solar system, but stepping beyond it. At infinity beyond, the outer solar system is not an ending, but a threshold. It is the last whisper of home before the cataclysmic silence of interstellar space. And as we send our machines, our messages, and someday even ourselves across this great divide, we become something new. Interstellar travelers, reaching for the stars. As we pass beyond the heliosphere and drift through interstellar space, our attention turns outward, toward the stars themselves and the hidden worlds that orbit them. For centuries, humans looked to the night sky and wondered, are there other planets like Earth? Are we alone? At infinity beyond, these questions are not just philosophical, they are scientific pursuits. And in recent decades, the answers have begun to emerge. The term exoplanet refers to any planet outside our solar system, orbiting a star other than the Sun. For most of human history, these planets remained invisible, their existence purely speculative. But everything changed in 1992, when the first exoplanets were confirmed, strange, massive worlds orbiting a pulsar. Then in 1993, the first exoplanet around a Sun-like star, 51 Pegasi b, was discovered. It was a gas giant in a tight, scorching orbit, unlike anything in our solar system. Since then, our catalog has exploded. Thanks to missions like Kepler, TESS, Transiting Exoplanet Survey Satellite, and powerful ground-based telescopes, we have now identified over 5,500 confirmed exoplanets, with thousands more candidates waiting to be verified. They range from hot Jupiters that skim the surfaces of their stars to super-Earths, rocky planets larger than Earth but smaller than Neptune. We found mini-Neptunes, lava worlds, and even rogue planets wandering between stars without any sun to orbit. But the most exciting targets are the planets located in their star's habitable zone, the region where temperatures might allow for liquid water to exist on the surface. These so-called Goldilocks worlds aren't too hot or too cold, but just right, and some of them orbit stars remarkably similar to our own. One such system is TRAPPIST-1, a red dwarf star about 40 light-years away, hosting 7 Earth-sized planets, at least 3 of which lie within the habitable zone. These planets are so tightly packed that if you stood on one, you could see your neighboring planet hanging in the sky, larger than the Moon appears from Earth. Red dwarfs like TRAPPIST-1 are smaller and cooler than the Sun, and much more common, making up about 75% of the stars in the Milky Way. This suggests that Earth-like planets could be far more abundant than once thought. Detecting an exoplanet is only the first step. The real challenge is determining its atmosphere and composition, and whether it might host life. This is where the James Webb Space Telescope, JWST, comes in. Launched in 2021, JWST has begun to study exoplanet atmospheres by capturing the faint light that filters through them as the planets pass in front of their stars. It can detect gases like water vapor, methane, carbon dioxide, and even signs of biological activity, known as biosignatures. Future missions like LUVOIR and HABEX may one day directly image Earth-like exoplanets, revealing their colors, clouds, and possibly surface features. If we find a world with oxygen, water, and methane coexisting in the atmosphere, it would strongly suggest biological processes, perhaps even life. At Infinity Beyond, we see each new exoplanet as a message in a bottle, a signal that the cosmos is teeming with possibilities. These distant worlds challenge our assumptions, expand our understanding of planetary diversity, and bring us closer to answering the age-old question, are we alone? The truth is, we've only just begun the search. With each passing year, our instruments grow sharper, our methods more refined, and our reach further. Somewhere out there, under the light of a distant sun, may lie another Earth, waiting to be found. The discovery of exoplanets has reshaped our view of the universe, revealing a galaxy brimming with strange and diverse worlds. But finding planets is only the beginning. At Infinity Beyond, we ask a deeper question, one that has echoed through millennia. Is there life out there? And if so, what might it look like? Here on Earth, life has proven astonishingly adaptable. It thrives in boiling volcanic vents, beneath Antarctic ice, and in toxic acid lakes. This wide tolerance suggests that life, at least in microbial form, could exist in a far broader range of environments than once thought. That idea has fueled the field of astrobiology, which seeks to understand not only where life might exist, but how we might recognize it when we see it. The basic requirements for life, as we know it, include liquid water, chemical energy, and organic molecules. These ingredients are surprisingly common throughout the universe. Water has been detected on moons like Europa and Enceladus, in the atmospheres of exoplanets, and even in interstellar clouds. Organic molecules, the building blocks of DNA and proteins, have been found on comets, in meteorites, and drifting in deep space. But what if alien life doesn't follow the blueprint of Earth? It's possible that life elsewhere could be based on different chemistries. Instead of carbon-based life that relies on water, alien organisms might use silicon, ammonia, or methane as their foundation. On Titan, Saturn's largest moon, surface lakes of liquid methane replace Earth's water oceans. Could some form of methane-based life thrive there, using a chemistry alien to everything we know?